Welcome everyone. My name is Nikita Kuzmin. I'm a PhD student at Nanyang Technological University, Singapore. Today, I'm going to present our system for VoicePrivacy Challenge 2024. I have done this work with my colleagues from NTU and Northwestern Polytechnic University. In contrast to previous system, this system description is focused on modifications of baseline system and some analysis. Also, we provided analysis of disentanglement-based model such as natural speech-free codec. I'll cover only models what were submitted for evaluation. Feel free to check our system description as it covers more experiments and insights. I'll start off with our motivation. We wanted to provide analysis of baseline systems and enhance privacy and utility metrics. Second, we noticed that baseline models are lacking of emotion recognition performance, so we wanted to work on this issue. Third, we have interest in disentanglement-based models such as natural speech-free codec, because this type of model is trying to disentangle information about speaker and speech content. I'll start with description of natural speech-free codec and our experiments connected to it. Here you can see the architecture of natural speech-free codec. It consists of encoder-decoder architecture with factorized vector quantization modules. It is trained with gradient reversal layer and in order to disentangle information. To apply this for VoicePrivacy Challenge 2024, we use pre-trained codec model and its outputs and pass speaker embeddings through anonymization model. The model uses averaged embedding taken from a pool of farthest embeddings with opposite gender to source speaker. In this table, you can see technical details about natural speech-free codec and anonymization module. This table shows the results for natural speech-free applied to VoicePrivacy Challenge 2024. First row corresponds to original codec without any anonymization. From the results, we can see that this model provides relatively high emotion recognition performance, but at the same time, there might be some speaker identity leakage in other branches, as echo rate is not that high. Next, let's move to experiments with baseline B3. I'll briefly introduce the baseline B3. It consists of procedure extractor, ASR model, and speaker embedding extractor. Anonymization of F0 consists in value-wise multiplication by a random value from specific range. Additionally, they have speaker anonymization implemented using Wasserstein GAN. For speech synthesis, they use FastSpeech2, and for audio synthesis, Hieu-Thi GAN. More detailed information about this model is displayed on the table on the left. The modified baseline B3 is illustrated on this slide. It's quite similar to the baseline with addition of emotion embedding branch and slight change of speaker and prosody anonymization modules. In this table, you can see the differences between modified baseline system and baseline system itself. The changes are highlighted in green. We used dimensional speech emotion recognition model based on WAV2VEC 2.0 for emotion embedding extractor. Also, for some our models, we removed prosody anonymization model because it provided better utility metrics. Additionally, we removed Wasserstein GAN by pool of vectors and random speaker per each utterance with cross-gender because it provided slightly better results. In this table, you can see comparison between baseline model B3 and modified baseline model. So when we add emotion embedding, we get better results for emotion recognition by 10% approximately, and keeping the same ASR performance, but also there is some leakage of speaker identity, probably in emotion embeddings, and it leads to degradation of our privacy protection. In this table, we show experimental results for different power of prosody anonymization. In first column, you can see multiple range for our prosodic features. From this table, we can see that we can tune trade-off between privacy and ASR performance by modifying power of prosodic features. It can be useful depending on our task, what our priority. Finally, let's move to baseline B5 and experiments. It consists of F0 extractor and ASR acoustic model with vector quantization and Hieu-Thi GAN as synthesizer. Additionally, they don't use any speaker embedding. They use just pool of one-hot and encoding vectors as speaker embeddings. On this slide, you can see the modification to the model. Weighted mean reversion of F0 and additive white noise. The formula for mean reversion is presented on this slide. It's just the weighted sum of original F0 and moving average. In our experiments, we used 32 frames for moving average. On this slide, you can see how F0 looks like after applying mean reversion to it in comparison to original F0 and moving average. This table shows the comparison between different alphas for mean reversion, and it shows that mean reversion actually helps to protect privacy with keeping utility metrics on the same level. And this slide shows F0 after applying mean reversion and additive white Gaussian noise to it. Here are results, and additive white Gaussian noise helps to push privacy even higher with keeping utility metrics on the same level again. It's important to note that during our post-evolution analysis, we noticed that the results with additive white Gaussian noise highly depends on how SV attacker model converges. Finally, to conclude everything, we will provide tables with comparison of submitted systems to baseline models, and also we'll highlight main takeaways from our analysis. First of all, we will compare our submitted models for condition 1 and condition 2 with equal rate higher than 10 and higher than 20, and compare it to baseline model 3, 4, and 5, and 6. We excluded baseline 1 and baseline 2 models because they do not qualify for condition 1, which requires having equal rate higher than 10%. So this table shows that natural speech free model provides a significantly better results for emotion recognition in comparison to baselines, but at the same time, it provides quite low privacy protection. Also, we highlighted in blue baseline B3 and its modifications of our submitted system. You can see that our systems 1B and 2A, which used emotion recognition embedding, boost emotion recognition a lot. At the same time, our system 2B outperforms baseline B3 in ASR task, and it still has higher than 20% equal rate. In this table, you can see comparison of our modifications of B5 with third corresponds to the model with mean reversion, and fourth corresponds to model with mean reversion and additive white noise. So we can see that mean reversion helps to improve privacy protection, and it keeps metrics pretty much the same. To finalize, I want to highlight following takeaways. First, about natural speech free FAQ logic. It provides promising results for emotion recognition in ASR task, but at the same time, there might be some leakage of speaker identity in other branches, like in the content branch or acoustic branch. Also, emotion embeddings helps to improve emotion recognition performance in comparison to baselines, but it leads to speaker identity leakage. Additionally, cross-gender anonymization improves privacy protection and emotion recognition metrics, but for some reason, it reduces ASR performance. And finally, mean reversion of F0 improves privacy protection while keeping ASR and emotion recognition the same, but at the same time, it's quite sensitive to convergence of attacker model. That's all. Thank you very much for your attention.